So far we have proved that kinetic energy is conserved if there's no external force and the collisions among the particles are completely elastic. Next, we're going to show the conservation of energy if we talk about the conservation, transformation of potential energy into kinetic energy. Now, we did that several lectures ago. As we said that if we have a concrete block at a height of h and a mass of m, it would have a potential energy of m times g times h. And if I drop, and initially, let's say the velocity of the cinder block is 0. If I drop the block, it would acquire a velocity before hitting the ground of v. And what we have shown the other time is basically conservation of energy of, in this case here, conservation of gravitational potential energy into kinetic energy. And we've shown in the last class that mgh, which is the gravitational potential energy, would that be equal to 1/2 of mv squared, the velocity that is acquired by the mass as it drops from a height of h ending in a velocity of v. Now, very quickly we can show this. Before that, let's just have a look at, again in this case here, going back to Newton's laws of physics, we said that the conservation of momentum is because of the first and the third Newton's law. First, that motion would remain if there's no external force acting on an object. And the third law says that action and reaction are equal and opposite. And together they would validate the conservation of momentum. Now, if you think about there's an external force F on these objects because of some sort of field, in this example here we're talking about gravitational field. The same principle will apply if you talk about electric field or magnetic field or any other kinds of field that is similar to gravitational field. So what we have is the field, we have a force vector, and the total force acting on all these particles will generate an acceleration of AI, a vector on the mass mi. Now, if you remember that momentum is defined by the sum over all particles of mass mi with its velocity vi. So if you differentiate the momentum, then the pi dt corresponding to the differentiation of the momentum with respect to time, summing over all particle I, what you have is that is from this equation here, you differentiate this, you have dvi dt, and that's the acceleration vector. So the force mi times ai would be equal to the sum total of the rate of change of momentum. Having said that, what we can show then how the potential energy of a force acting on mass m and an acceleration of a would do a work W equal to F times D equal to F m times A times D, or MAD here. And again, we said that D is equal to 1/2 of AT squared. And if you rearrange the term, that's 1/2 of AT in bracket square, and that's equal to 1/2 mv squared. And the conservation of energies from the kinetic, from the potential energy into kinetic energy is very simply a definition resulting from the work equal to F times D, and also the definition of displacement and velocity as a function of a constant acceleration. So you have this conservation of gravitational potential, converting that energy into kinetic energy. So we likewise can prove that other kind of potential energy, such as electrical potential, gravitational potential, since they also, as we shall describe later, cause an acceleration on electric particles or magnetic particles. And therefore, would also give you this conservation of, say, electric potential into kinetic energy. Now, then you can talk about conversion of electrical energy into gravitational potential energy also, but that is just having the kinetic energy in between. Now, there are other forms of energy which we have so far not described. For example, heat energy. And ultimately, heat energy is really kinetic energy of microscopic particles such as molecules on a microscopic scale. And given the collision of molecules is largely elastic, and therefore what we have in that case would also a conservation of kinetic energy. If the collision of gas molecule is elastic, the heat would remain the same for that system. That we shall describe a little bit later, but here the conservation of energy is a very general law of nature. Nothing violates that, no matter what kind of energy we're talking about, largely because I think the term of energy is defined by W equal to F times D. So force is really the intermediate agent whereby energy of different form, whether kinetic or potential or heat, will be transformed into other kinds of energy.